Hello. Hello. Hi. Am I audible?
Yes, you are.
Okay. So let's start with this week's tutorial. Hi, I am Pankaj Kapli, an NPTEL PMRF TA, and I'll be discussing some problems related to this week's video lectures. And the problems are based on mostly the solving system of linear equations and some concept about vector spaces and their subspaces and linear independence of vectors. Okay, so let's see the first problem. Okay, so this is our first problem. It says that we have to choose which options are correct out of these four, and a system of linear equations is given, and we have to find if this system has unique solution or infinite number of solutions, or if it has no solutions. Okay, so how do we solve this system? So basically we have to, if at all values of x1, x2, x3 exist, then we have to find these values, or if their values doesn't exist, then we say that there are no solutions of the system of equations. Okay, so what we'll do first, we write the system in a matrix form. Okay, uh, that is what we'll do, just write this system in matrix form. So that is, we'll write it as ax equal to b. Okay, so where a is will be a matrix. So what is this matrix? This is a coefficient matrix. So we just choose coefficient of x1 as a first column. So 2, 1, 2. Coefficient of x2 in the second column. 3, minus 4, 2. And coefficient of x3 in the second column. Minus 1, 10, 5. Okay, then your
It
x
should be it should be 3 minus 4 1 minus 1, sorry.
2 minus 1, and yes, so 2 minus 1, 5, right? So 2 minus 1, 5, and x1, x2, x3, and that is our equal to the vector b, which is 5, 2, 3. Okay, note that this system of equations actually equal to this matrix equation. So, or you can say it as vector equation, where we multiply this matrix A with the unknown vector x, and we get the vector b, and we have to find if this solution exists for this system, then we have to find the value of x. Okay, so what we'll do, so there is one method which is called Gauss elimination method, and in this particular method we take this augmented matrix. So what is our augmented matrix? With A side by side we write b vector also, and we just take this particular matrix and we'll apply some elementary row operations and reduce this particular matrix in a very special form, and that particular form is called a row echelon form. Okay, let's see what is in row echelon form by this example. Okay, so let's write augmented matrix. So what is our augmented matrix? AB. So 2, 3, minus 1, the first row. 1, minus 4, 10. The second row. 2, minus 1, 5 in the third row. And side by side we write this B vector also, which is 2, 5, 2, 3. Okay, then what we'll do, we'll try to make all the entries below the main diagonal 0. So that means we'll try these entries become 0, these things. Okay, so and then we will see then if these entries will become 0, then we'll call that particular form as row echelon form, and there will be some non-zero and 0 entries on the main diagonal. Okay, so that will do by some elementary row operation. So what are elementary row operation? We can change two rows. That means we can always interchange two rows, and that is equivalent to just writing your system of equations in a different order. Okay, and you can multiply any row by some scalar. That is exactly writing the same equation by multiplying some scalar both sides. And what we can do, we can add to a row some scalar multiple of another row. Okay, so that we do sometimes to eliminate a particular variable. And whenever we apply elementary row operation, we'll just write this equivalent symbol. Okay, so what should we do in this particular case? Okay, so you can see that this particular 2, we can make it 0. How? By subtracting first row from the third row, right? If you subtract first row from the second row, then this particular entry of this matrix will become 0. Okay, so this in symbol we write elementary operation that R3 is going to change to R3 minus R1 in this particular symbol. That is, we are changing R3 to a new row. The row 3 is changed to this new row, and that row is row 3 minus the row 1. Okay, so let's see what that is. Okay, so all these rows are as it is: 2, 3, minus 1, 5, 1, minus 4, 10, 2. Just subtract from the third row first row. So 2 minus 2 is 0. Minus 1 minus 3 is minus 4. 5 minus 1, which will be plus 1. So it becomes 6. And 3 minus 5 is minus 2, right? Okay, so this is our equivalent matrix. Now we'll again apply another operation. Okay, so what we'll do, we just multiply second row by 2. Okay, so let's multiply this row, the second row by 2, so that this entry will become 2, and then we will subtract from this the first row. Okay, so this in symbol we can write that R2 we are changing by 2 times R2. 2, 3, minus 1, 5, 2, minus 8, 20, 4, 0, minus 4, 6, minus 2. Okay, so now what we'll do, we'll subtract from second row the row 1. Then what we'll have, this will become 0. So minus 8 minus 3 is minus 11. 20 minus plus 1, so it will become plus, so it's 21. And 4 minus 5 is minus 1. 0, minus 4, 6, minus 2. Okay, now we'll try to make this entry 0. And how do we do that? Okay, first let's make it 1. Then we can multiply by 11, and then we will subtract. That means what I'll do, I'll divide third row by minus 4. That is equivalent to multiplying the third row by minus 1 by 4. Okay, so let's do that. What will we have? 2, 3, minus 1, 5, 0, minus 11, 21, minus 1. Okay, so divide the third row by -4. So what we'll have is 1. This will become -3/2, and this will become half. Okay. Now we'll multiply the third row by 11. Okay, let's multiply third row by 11. Again, R3 will change it to 11 times R3. Then what we'll have 2, 3, -1, 5, 0, -11, 21, -1, 0, 11. So this is 33/2, and then 11/2. Okay. Now we will add second row to the third row. So again, R3 we change it to R3 plus R2. So 2, 3, -1, 5, 0, -11, 21, -1. Just add these two rows, the second and third row. So this will remain 0. This will become 0. Okay. So what is 21 minus 33/2? It's 9/2, right? Okay. What is 11/2 minus 1? Again 9/2. Okay. So this is our echelon form. This is called row echelon form. Okay. Why this is called row echelon form? Because you notice that this is our main diagonal, right? This is our main diagonal, this thing of this 3 by 3 matrix, except this column. This is our augmented matrix, and below this main diagonal everything is 0, and that's why we call it a row echelon form. And then we will check how many non-zero entries are there on the main diagonal. Okay, now you can see that there are 3 non-zero entry on the main diagonal, and we have 3 unknown variables to solve. That means the system is consistent and there will be a unique solution. Okay, and that's why one of the answer is B, that the system has a unique solution. Now let's find that unique solution. Notice that why this particular form is useful, because it makes other variables 0 and only one remaining. You can notice that in the third row you will have 9/2 x3 is equal to 9/2, and that will give you x3 is equal to 1, right? So that it is easy to solve. Again, you see that second row just become 11x2 plus 21x3 equal to -1. But now the value of x3 we know, right? Because we have already solved the third equation, and that will help us to find the value of x2. Okay, just put value of x1, which is 1. So this is -11 plus 21. So 11x2, which is -1, and that will imply that x2 is 2, right? And now we have the last equation, which is just 2x1 plus 3x2 minus x3 is equal to 5. Now we know values of x2 and x3. So this will become 2x1 plus, so x2 is 2, so it's 6, and minus x3 is 1. So 6 minus 5 is 5 is equal to 5, and this will imply that x1 is 0. Okay, so we have our answer that there's a unique solution, and the solution is x1 is equal to 0, x2 equal to 2, and x3 equal to 1. That is our option B and D are correct. Okay, that is the first problem. So are there any questions regarding this problem? You can ask if there are any questions. Okay, so if there are no other questions, let's move to the second problem. Again, the second problem has the same type. You have another system of equation, and now you have to find out if the system is consistent or it has some solution or not. Okay, so again, just write this into the matrix form. So if you write this as ax equal to b, what is our a? Will be 1, 3, minus 1, 2, minus 3, 6, 0, 9, and minus 8. So again, x1, x2, x3, which is equal to minus 1, 7, and 9. Okay. Now we'll consider again same augmented matrix. So what is our augmented matrix? A by B is okay. So again, let's reduce it to a row echelon form. Notice that we already have a 0 entry. So our aim is to make this entry 0 and this particular entry 0. Okay. So let's apply these elementary row operation. Okay, how to make this thing 0? Okay, so what we'll do, we divide this particular row by 3, because if you divide by, this is 9, if you divide by 3, this will become 3, then we can add these two rows so that this entry will become 0. So let's divide first R3 by 3. What we have, 1, 3, minus 1, minus 1, 2, minus 3, 6, 7, 0, 3, minus 8 by 3, and this is again 3. Okay. Now you will notice that if you add these entries, basically we are not just adding entry, we are adding these two rows, then this will become 0. So what we do, we'll change row 3 to the sum of row 2 and row 3. But we'll get 1, 3, minus 1, minus 1, 2, minus 3, 6, 7. This will become 0. Now what is 6 minus 8 by 3? That must be 10 by 3, right? And then we have 10. Okay. Now we have to make this thing 0. Okay, let's divide it by 2. If we divide it by 2, this will become 1. Then we can subtract first two rows to get to make it 0. So let's first divide R2 by half by 2, and this will give us 1, 3, minus 1, minus 1, 1, minus 3 by 2, 3, and 7 by 2, 0, 0, 10 by 3, and 10. Okay. Now notice that if we subtract these first two rows, then we can make this entry 0. This particular entry we can make it 0. So let's do that. We change R2, the second row, to R2 minus R1. So first row will not change. This one. Subtract. If we subtract, what will have? This will become 0. Okay. Now what is minus 3 by 2 minus 3? It is minus 9 by 2. This will become 4. This will again become 9 by 2. we have this 0, 0, 10 by 3 and 10. So we have made some mistakes. See, this is -9. Okay, so here we have to write -9. So this was -9. So that must be -3 because we are dividing by 3. Then we are adding the row 2. So this will become 4. Okay. There is another mistake. While we are here, we are adding our row 2 and row 3. So you can see that this will again become non-zero. So we should not do that, I think. Okay, let's do one thing. Notice that if we change row 3, then this entry was 0, then it will become non-zero. So we will not change row 3. Instead, we'll make a change in row 2. We'll make a change in row 2. Okay. So we are changing row 2 and we are adding 2 rows. So this is again 2. This will become 0. And 6 minus 8 by 3. And this will become 4. And we have 3 minus 8 by 3 and minus 3. Okay. Now what we can do, we have already divided second row by 2. That is correct. So if we divide second row by 2, then we have 1, 0. This is 5 by 3 and 2. Okay, now okay. What we'll do now, we will interchange 2 rows. We will change 2 rows. So when we interchange row, we write it like this. So what we have, if we interchange row 1, 3, minus 1, minus 1, this row will go above minus 8 by 3, minus 3, and this will come down row, second row. So 1, 0, 5 by 3, 3, and 2. Okay. So now we want to make this entry to be 0. So what we'll do, we subtract first row from the third row. So we'll change third row and we'll subtract row 1 from it. And this will give us 1, 3, minus 1, minus 1, 0, 3, minus 8 by 3, and minus 3. So if we subtract this 1 minus 1 will become 0. And now 0 minus 3, it will become minus 3. 5 by 3 plus 1, this will become 8 by 3. And this will again become 3. Now notice that the second row, the second and third row, they are just differ by a multiple of -1. So this says that basically these two equations are same. So there is a redundant equation. Redundant means the equation is repeated two times. The same equation is repeated two times. So the equation is not necessary. Okay. So at the end, in short, there are two equations and three unknown variables. So if we have two equations and three unknown variables, that means that there must be infinite number of solutions, right? Why? Because there is always one variable which we can choose freely, whatever we want, whose value we can choose whatever we want. So you can see that what we'll do, we can add two rows, R3, we can change R3 plus R2, and this will give 1, 3, -1, -1, 0, 3, minus 8 by 3, and -3. This will become 0, 0, 0. Now you can see that the third row, the meaning of third row is nothing because this is a zero row. So that means a zero equation, 0 equal to 0 form. So there is nothing. So there are only two equations. The first row will give equation 1, the second row that will give equation 2. So there are two equations, three variables. That means there are infinite number of solutions. Okay, so that's why the correct answer here is there are infinite number of solutions. Okay, let's go to the question 3. This is again same kind of problem, but here instead of numbers you have these variables a, b, and c, and now we have to see under what conditions or what condition we put on a, b, c so that this system of equation has either infinite number of solutions or a unique solution, or when does the solution of the system exist depending on values of a, b, and c. So let's see what condition on ABC we have to put. Okay. Okay. Again, we write this in a matrix form. So in this case, this is -2, 1, 1, 1, -2, 1, 1, -2. So this is our system. This is equal to ABC. Okay. Again, let's write augmented matrix. Okay. On the diagonal, we have -2 and everything is 1, 1, -2, 1, 1, 1, again -2, and this is A, B, and C. Okay. We have to make these things 0. Let's make these three entries 0. How do we make these entries 0? So let's first target this first entry, and this can be made 0 by subtracting second row from the first row, from the third row. So we are changing third row, R3 minus R2. So -2, 1, 1, and A, 1, -2, 1, B. This will become 3. This is -3. C minus B. Okay. Let's make this entry 0. So how we can make this entry 0? Or let's make first this entry 0. So first we'll do just multiply second row by 2. Second row is changed to 2 times second row, and that will give us -2, 1, 1, A. So 2, -4, 2 twice of B, 0, 3, -3, and C minus B. Okay, now you can see that we can add first two rows and we can change the second row so that this entry will become 0. We are changing R2 to R2 plus R1. This will become 0, -3, 3, and A plus VB is 0, 3, -3, and C minus B. Okay. Now we just add these two rows so that this entry will become 0. So what we'll do, change R3 by adding R2 to R3. Okay, so what we have here, -2, 1, 1A. This will not change the second row. Now add third row to the second row. Add second row to the third row. So this is 0. This will again become 0. This will also become 0. And this will become A plus B plus C. So this is our system, which is in the reduced echelon form, right? Because these three entries are 0. And now you can see that there is in our augmented matrix, this, on the diagonal, this third entry becomes 0. So this, if this third entry becomes 0, that means that what is our third equation? Our third equation says that 0 times x3 is equal to so 0 times x3 is equal to a plus b plus c. Okay. Now notice that if a plus b plus c is non-zero, let's say this is non-zero. Okay. Then you can see that the right hand side is non-zero, but 0 times x3 is always 0, right? And a non-zero entry cannot be 0. So that is the contradiction here. That means that a plus b plus c must have to be 0 so that there is a solution. Okay. If a plus b plus c is non-zero, then there are no solutions. Or this just implies that for solution to exist, a plus b plus c must be equal to 0. Okay. So we have to see which of the following options are true. So note that solution exists if a plus b plus c is 0. So this is true because in this case solution will exist. This is false because this is just in this case there are no solutions. And you can see that solutions are not unique. Why solutions are not unique? Because if a plus b plus c becomes 0, if this equation becomes 0, then this will become 0, right? That again means that there is two equations with three variables. If there are two equations with three variables, that means there are infinite number of solutions. So solution is not unique. Okay, and if saying that if solutions exist, then the rank of the augmented matrix is 3. Notice that this is also false because the rank of the augmented matrix is here 2. So what is the rank? Rank means how many non-zero entries are there on the diagonal. So there are only 2 non-zero entries. Therefore, rank is 2. Okay, let's start with the fourth problem. So most of the problems are solving the system of linear equations. So this is a different problem. Wait 2 minutes. I think my internet connection is down. Okay. So let's start with the fourth problem. So in this fourth problem, we have to say which are subspaces of the specified vector space. Okay. So what are subspaces? Or let's see first what are vector spaces. Okay. So vector space is just a set with some operations. Like so, it's a collection of vectors. So what is a vector space? We can understand it like it's a collection of some vectors. Okay, with some additional properties. So these are just vectors. So V is a vector. Okay, so vector can be anything. It can be a vector in R3 or R4 or Rn. So it's a tuple of real numbers, or as a vector there can be other non-trivial elements also, like polynomials. Okay, so we'll see one example with polynomial. And what this collection has, so this is our vector space, and we say that this collection has two operations. So what are those operations? One is we can add two vectors. So whenever we add two vectors, the vectors will belong to V. And we can also multiply any vector by some scalar. Scalar means there is some real number or complex number that we can multiply. So for any vector, the C times V, this is called a scalar multiplication. This is also in there inside our vector space, and they satisfy some additional properties. Okay. So in that case, we say that this V is a vector space over R. So what are those properties which vector space satisfy? So the first property we can say that, okay, that whenever we add three vectors, let's say V plus, if we are adding two vectors, three vectors, so this property says that we can add these vectors in any way. So we can first add V1 and V2 and then we add V3, or first we add V2 and V3 and then we add V1. That is the first property. Second property, we can say that there is a zero vector. Okay, so it says that there exists a zero vector inside V, such that, so what property zero vector has, whenever you add zero, it will give the same vector, or 0 plus V. There is a third property. We say that for every vector there is a negative vector. That means that for every vector V in our vector space, there exists a negative of vector in vector space, such that when we add them, when we add these things V and minus V, we get our zero vector. The fourth property says that we can add vector in any way. So either first add V to W or add W to V. So these are properties of additions, and there are some properties of scalar multiplication. So what are those properties? We can say that if we have two scalar, let's say C1 and C2, if we are multiplying like that, you can change the order also. That is C2, C1, V, or you can multiply C1, C2 first, and then we can multiply by V. That is one of the properties of scalar multiplication. And there is another property of scalar multiplication that says that C1 plus C2, if you multiply to a vector, so these are called distribution properties. That is C1 times V plus C2 times V. Okay, there is another property of distribution which says that if you multiply a scalar with sum of two vector, let's say V plus W, then this is equal to CV plus CW, right? You can notice that these properties are quite obvious for the vector spaces or R2, R3. But in general, these are some abstract properties we put on a set, and if a set satisfies these properties, then we say that the set is a vector space. Okay, so what are subspaces? Okay, so subspace means a subset of a vector space which is itself a vector space. Okay, so let's say V is a vector space, and this W is a subset of V. Then if W is a vector space, under operations, so the operation of addition and scalar multiplications of V. So under the operations of V, then we say that W is a subspace of V. Okay, so how do we determine if a subset is a vector space, is a subspace of a vector space or not? Okay, so there are two properties that we can always check. So first is, if we are taking two vectors from the W, their sum must lie inside W. So these are two properties we check, and the multiplication of this scalar multiplication of a vector from W must belong to W for all V lying in W. So these two properties if you check if these two properties holds for a subset, then we say that that particular subset is a vector subspace or a subspace of the vector space. Okay, so let's see in which cases these properties hold. See, there are we have given two subsets. Okay, so what is our vector space here? So vector space is R3. Okay, you can see that all these vectors lies in R3. These are subsets of R. Here in this case subset is R2. Here subset is R4. Vector space is R4. Okay. W1 is a subset of R3. W2 is a subset of R2. W3 is a subset of again R3, and W4 is a subset of R4. And we have to see which of the following subsets are not subspace. We have to find which are not subspace. Okay. You can see that the W1 consists of those vectors where the second entry is non-negative, right? The definition of W1 is given by this that the second entry must be non-negative, right? Okay, so does it is it a subspace? It cannot be a subspace. Why? Because if you take this scalar -1, right, you can always multiply by -1 so that this entry will become negative. Okay, so if x1, x2, x3 belongs to W, then -1, just multiply this -1 with this vector x1, x2, x3. This does not belong to W. Why? Because if you multiply -1 to x1, x2, and x3, then you will have -x1, -x2, and -x3, right? Because this vector belongs to W, that means that x2 is non-negative, and since x2 is non-negative, -x2 must be less than equal to 0, right? So if we take x2, let's say let's choose x2 to be 1. Okay, so if x2 is 1, then this will become -1. And this is, and therefore this is not a subspace. Okay, so W1 was x1, x2, x3 in R3 such that x2 is greater than equal to 0. So why W1 is not a subspace? Because you can see that this 1, 1, 1, this belongs to W1, but -1, -1, -1 does not belong to W1, and therefore W1 is not a subspace. This is first one. What is W2? This is all those xy in R2 which satisfy this equation. So what is that equation? That y is x cube. So it's y is x cube or x is y cube. Yeah, y is x cube, right? Is it a vector space? Can it be a vector space or not? Okay, let's find out if it is a vector space or not. First, find some element of W2. That means some two numbers which satisfy this equation. Okay, we can take 1 comma 1, right? Note that 1 comma 1 belongs to W. Why? Because 1 is equal to 1 cube. Okay. And we can take some another vector. What we can write? You can see that 0 comma 0. Okay, let's not take 0 comma 0. We just multiply this by 2. If you multiply by 2 this vector 1 comma 1, what will get? This is 2 comma 2. Thus 2 comma 2 belongs to W2. This is not. Why? 2 comma 2 does not belongs to W2 because 2 is not equal to 2 cube. The 2 cube is 8. This will become 8 and 2 is not equal to 8. And something which lies in W2 must satisfy this equation that the y coordinate is the cube of the x coordinate, and that does not happen with 2 comma 2. So the scalar, if you multiply the vector by some scalar, then the resultant vector is not there inside the W2, and therefore W2 not a subspace of V. Okay, so instead of V, let's write R2, not a subspace of R2. Okay, what is the third one here? W3. First two entries are same. So x1, x2, x3. In R3 such that x1 is same as x2. Okay, is it a subspace of R3 or not? Okay, notice that this is a subspace. Why this is a subspace? Let's check those two conditions. Which condition we have to check? We have to check if we take two vectors from W to W3, then their sum lies in W3. And if we take something scalar multiplication time some vector, then that should also lie in W3 for every vector in W3 and this scalar in R. Okay, so let's take two vectors V comma W from W3. Okay, let's write V as x1, x2, and x3, and W as y1, y2, and y3. Okay, since V and W belongs to W3, that implies that the first entry should be equal to the second entry, and here also first entry must be equal to the second entry. So what is V plus W? So V plus W is x1 plus y1, comma x2 plus y2 and x3 plus y3. Okay, so if we have to find out if first entry is equal to second entry or not. Okay, note that since these two equations hold, they will imply that x1 plus y1 must be equal to x2 plus y2, and therefore this will belongs to W2 or W3 because the first entry is equal to the second entry here. These entries are equal. Okay, and now we have to check for scalar multiplication. Okay, so let's take C in R, real number, any number. So what is C times V? It's C times x1, C times x2, and C times x3. Okay, so this vector also belongs to W3. Why? Because Cx1 is same as Cx2. Because x1 is same as x2, therefore when you multiply x1 and x2 by C times x1 is same as C times x2, and because first and second entries are same, that means C times V is also in W3, and therefore W3 is a subspace of R3. Okay, Now let's check for the last one. What was the last one? The sum of the first two entries is 1. X1, X2, X3 in all these entries in R4 such that the sum of first two entries is 1. Okay. And is it a subspace of R4? So this is not a subspace of R4. Why? Because you can see that it says this the definition is given by uh, that if you add these two entries, the first two entries, the x1 and x2, their sum must be 1. Okay. So what we have to do, we just take some vector from W4 where the sum of the entries is 1, and we multiply by it some scalar so that the sum of the entries will become like not, it will not equal to 1. That means that the if you multiply uh, some vector by a scalar in W4, then the resultant outcome is not lie does not lie in the W4, and that means W4 cannot be a subspace of R4. Okay, so what should we take? Okay, let's take this vector 1 comma 0 comma 1 comma 1. Okay, this belongs to W4, right? Why? Because the sum of first entry and second entry is equal to 1. Okay, what we'll do, we just multiply it by 2. This is our V. So what is 2 times V? It will become 2 0 2 comma 2, and this cannot belongs to W4. Why? Because the sum of first two entries 2, and which is not equal to 1. So therefore W4 is not a subspace of R4. So what are correct answers here? So A is correct because this is not a subspace. B is correct, this is not a subspace, and D is correct. D is also not a subspace. Only C is a subspace, the vectors. Okay, let's move to the next problem. This is again based on the same topic. A vector space is given and a subspace is also a subset is also given, and we have to find if that is a subspace or not. Okay, so here what is our vector space? So our vector space is P4. So what is P4? P4 means it's a all polynomials. So all polynomials of degree less than or equal to 4. So what do we mean by polynomials of degree less than or equal to 4? We mean by a0 plus a1 times x plus a2 times x square plus a3 times x cube plus a4 times x cube power 4. Okay, so these are our vectors. So here our vectors are polynomials. Okay, and these are entries a0, a1, a2, a3, a4. They all are real numbers. Okay, and this P4 is a vector space over R. Why this is a vector space? Because if you add two polynomials of degree less than equal to 4, then you'll get again a polynomial of degree less than equal to 4. And if you scalar multiply by if you multiply a polynomial by some scalar, then you'll have again a polynomial of degree at most 4. So you can check that all the properties of vector space get satisfied here, because you can add two polynomials in any way, and you can. Okay, so this is a vector space, and a subset of P4 is given. So what is that subspace? So W is equal to all those polynomials fx in P4 where if you put 1 instead of x, then this f of 1 belongs to the set of integers. So that we denote by z. That means it's either a non-negative natural number or it's a negative number. Okay, and we have to find if this is a vector space or not. Okay. Okay, which one of these two is this correct? 0 does not belongs to W. Can 0 be there inside W? Okay, you can see that 0 is there in P4. Okay, so 0 is there in P4. So let's take our function f of x to be 0 function. So this is 0. So if you put anything, this will give 0. What is f of 1 here? F of 1 is also 0, and 0 is also integer. So 0 belongs to z. So it's an integer. That will imply that 0 belongs to w. Okay, so because 0 belongs to w, that means this option is not correct. So this is wrong. Okay, so if we have two elements f and g from w, is it true that there's some lie inside w? Okay. So what I'm saying that if you take two polynomials f and g from w, because f and g are w, that implies that f of 1 and g of 1 belongs to integers. And if you add two integers, f of 1 plus g of 1, they also lies in z, and that is f plus g of 1, which is equal to f of 1 plus g of 1, that also lies in z. So that is also integer. And this will imply that f plus g satisfy the definition of our set w, that is f plus g belongs to w. Okay, so this means this is also incorrect. This is also incorrect because f plus g belongs to w whenever f and g are in w. Okay, so this is also wrong because w is actually a subset of P4. W is a subset of P4, so this is also wrong. Now we have to check about this option C. It says that if f is in W and you take something C as a real number, it says that CF does not belong to W. Okay, you can see that this is correct. Why? Because if we have, let's say, some polynomial fx, so let's say what is let's take a constant polynomial. Let's say f of x is equal to 1. Okay, then this is belongs to W because it, it is a constant function and it takes value 1. Okay, but if you multiply it by some scalar which is a which is not an integer, okay, so you can take any integer, so we can take half. Let's multiply it by half, 1 by 2. So if you multiply function by half, so what will have at x, this will give half. Okay, and this half does not belongs to z, it is not an integer, and that will imply that half of this polynomial does not belongs to w, and therefore the option C is correct. Okay, so that's all for this week. So I was able to solve only 5 problems, but these problems take much time and our time is over. So we'll just end our live session here. Thank you everyone for joining this session. And we will meet next week with a new set of problems, okay, from the problems based on the lectures videos of the next week. So thank you everyone for joining.